to start the next chapter here. Your test is going to be next Wednesday. And I'm going to bring the test with me on Friday, so I'm going to give it, so it should be in your box over there. Okay? So it should be in your box. And that way we'll have the text next Wednesday. And it will be over chapters 4 and 5. On WebAssign, since we have met last and talked about the issues in WebAssign, something happened in WebAssign on October the 6th. What it did, for those of you who actually pulled over grades into the grade book, first of all, those grades were never added into your grade, so if you're looking to find out exactly where you stand in class, look at the weighted percentage for your grade, okay? Look at the weighted percentage for your grade. So even those WebAssign scores that came over, what it did was it dropped your, if you had, and even if you had merged your email accounts in the Cengage system or in the WebAssign system, it dropped the account that wasn't a student.noc.edu. And I actually added you back into class, or if you run into this problem again, re-enter the class key. For whatever reason, that's what happened, and apparently math has been experiencing something similar, and people just re-entered their class key and went back on, and things seem to work fine. We are working with Cengage to figure out exactly what happened. We do not know what happened. Cengage doesn't even know what happened. But we flagged the problem, and we've gotten at least for right now, it's cleared up. So, but double check your grade in Blackboard to make sure it corresponds to your WebAssign grade that you see for that assignment. Because I manually type those in, so sometimes there will be a typographical error, or a number didn't get, I'll enter only one digit, or something will be a little haywire. Just email me and I will go back and verify and look at it to make sure that we've got it covered. But you look at your weighted percentage of grade, because I'm going to get midterm lab grades here pretty quick, and we are at midterm, so we will be reporting midterm grades. That way you get a good idea of exactly where you stand. Questions about grades in WebAssign and grades in Blackboard now that we've gone through this little snag? Okay, all right. So let's work a couple of the most missed problems. I will tell you that the suitcase problem is actually on Blackboard, so there's another solution to it, so you can actually look at it. But this one was apparently the one that was giving people trouble. Is I had a crate, so there's my crate, and I had a force that was being applied to the crate, and this was at 20 degrees. So that was my 20 degrees, and that when I had a force, another one that had the force.
Not seeing the dot cam.
Oh, not seeing the dot cam. Okay. There we go. Okay, so we had a force that's being pushed along the floor at an angle of 20 degrees below the horizontal, as shown in the figure. Okay? So we've got a force that's being at an angle of 20 degrees below the horizontal, being shown like the figure. The figure is not giving you the exact same picture. Force being pushed across the floor at a constant force at an angle of 20 degrees below the horizontal. Was it the picture that was giving you guys problems? Who had problem with this one? Because basically, what you end up with, because you've got the force being applied, the way the question's worded doesn't match the picture, but the intent of the question is this. You've got your crate, you've got the force being applied, and this is 20 degrees. The way the question's worded, it's not that, but that's the picture. So if you worked off the picture, you did it right. If you worked off the way the question was worded, you obviously were going to have trouble. But what I've got here is I have my force. If I look, there's no acceleration. It's traveling at a constant velocity. So I have no acceleration in the x direction. I have no acceleration in the y direction. And so I look at the summation of my forces in the x direction. That's going to be the force times the cosine of the angle minus my force due to friction. And that's equal to 0. Because I have no acceleration in the x direction. And then I've got my summation of force in the y is going to be the normal force minus my force that's being applied minus the weight of the box is equal to 0. Okay? So I've got a force, and I've got the weight, and I have my normal force. Because if I draw my forces in the y, this is my weight, there's my normal force, and then I have this force in the y direction that's being applied. Oops. Let's do that. That way we have more paper. And we know that, so if I solve and I put in my force that I was using was 350 newtons. The weight of the box was 1,040 newtons. So now I can just plug in my numbers. So if I do my 350 cosine of 20 degrees is going to equal my force due to friction. And if I plug that number in, I get 329 newtons, because that's 350 newtons. If I do this one, the second one, and I solve for force, solve for the normal force minus 350 times the sine of 20 degrees minus the weight, which is 1040. This gives me 1.16 times 10 to the third newtons. So now I know that the normal force is that. Then we go back to friction is fun. Force due to friction, coefficient of friction times the normal force. So the force divided by the normal force is going to give me my coefficient of friction. So I'm going to take my 329 newtons, divide it by my 1.16 times 10 to the third newtons, and then I get my force, my coefficient of friction. My coefficient of friction is going to equal 0.284. And newtons cancel, and I actually get a ratio. So that was part A. And then they asked you, we're going to pull the block. So now we're going to pull the block with the same force. And we want to calculate what the acceleration would be for this one. So now I have to deal with this one. So I'm going to get the sum of the forces. I'm going to get the same equations that I had before, except now I get the acceleration in the x direction is equal to the force cosine of 20 degrees minus the force due to friction. And I can plug in my numbers, and I will get my acceleration as 0.640 meters per second squared. And I can get the mass. Remember that the weight is my mass times my acceleration. This acceleration is gravity. So what I would do is take the weight divided by gravity to get my mass to be able to plug into the problem. Okay? So using the picture, we can solve it, but if I read just the question, I have an issue there. All right. this problem. You had a pulley. So there's the pulley. We have a bowling ball off of one side, and we have a pail, and we have a second pail. Okay, we have a bowling ball, pail, and this is going to be mass 1. This one is mass 2. This one is our 3 kilogram mass. Okay, or mass 3. So if I look at each one of these, I'm going to get 3 equations, because this one is going to be the summation of the forces in the y direction is my tension and my weight. And so if I write my summation of forces problem for mass 1, that's the mass 1, the acceleration 1, is equal to this tension, and we'll call this tension 1 just to keep track. Double check and make sure we didn't lose anything with that particular ding. So I've got that one. So now if I look at this one I have the weight. So this is mass 2. I also have the tension in this one. So there's my forces, and so this is the tension T2. I've got it pulling down here, and I've got it pulling up there. So I've got T2, and then I have T1 going up. So now if I do the summation of forces for 2, I get mass 2, acceleration 2 is equal to T1 minus mass 2, gravity, minus T2. Now if I look at the third one, I have the weight, I have the tension T2, and then I have acceleration. So now I've got F3 is equal to mass 3, acceleration 3, T2 minus M3G. But because the system is connected all together, A1 equals A2 equals A3. Okay? So that's how you set that problem up. Now, to help you guys out, because I've been working with some folks and various things, looking at how to work some of these problems. When you're given a problem in WebAssign, so here's my problem. I'm going to focus it here. Maybe. Okay, I want to zoom in, and now I can't zoom in. There we go. So when I print the problem out, and I recommend you do this, I recommend you go ahead and print your problems out. When you first get on WebAssign, go ahead and print your problems out. Does a couple of things for you. One is if your internet's down, you at least have a paper copy of what it is, the problem that you're working on. 2, if you're on the bus somewhere, going from point A to point B, you gotta be, and you don't have your internet access, you got something to work on. And it gives you a place that if something does fall apart, that you have a backup that you can take a photograph of it and send it to me. So there's a lot of reasons why you want to print these out. But the other reason you want to print these out is this right here. That little code right there. Because what WebAssign does is it will give you randomized numbers, but this corresponds to the end of chapter problem. Okay? So if I were to take out my book and look at my book, this tells me that I'm in the 11th edition, which that's your book, okay? We're using the problems from your book. This part tells me which chapter it is. So that number 4, we're in chapter 4. So that tells me that at the end of the book, I've got the chapter number right there. And this tells me what problem it is. So if I go to the end of the chapter and I look at the problems, this problem is going to be problem number 78 at the end of the chapter. Okay? So this problem, if I go into my text and I look at it, I get problem number 78, then it gets me to the end of the chapter. Well, WebAssign gives you random numbers in there, but your book doesn't. Some of the homework problems are give you the answers in the back of the book. So I can go to the back of the chapter, read this question with that number, and then I can double check to see if there's an answer in the back of the book for that number. And then I can use that to figure out how to do this problem without using a try in WebAssign. The other thing it does is, if you remember how back of chapter problems work, you'll get a title, and then you'll get a series of problems. And then you'll get another section title, and you get a series of problems. This title corresponds to a section in the text. And most of you have probably figured out that if this is 1, 2, 3, 4, 5, problem 1 is usually the easiest problem associated with the information in the text. Problem 2 is usually a little harder. Problem 3 is a little harder yet. Problem 4, and usually the last one down there is the hardest of that section. So if I'm having trouble understanding a concept, or I'm having trouble with a problem in that text, I can use that section to help me figure out that problem. Now, towards the end, you'll have challenge problems and you'll have other problems in there, but at least you can kind of go back and say, where is it that I'm having an issue? Because the other thing that you can do is, even if that problem that you were given, I don't have it in the back of the book as a solution to go double check my answer, which is one of the reasons we like to use WebAssign, because it gives you randomized numbers and make sure that you understand how to work the problem. I can look at the problems on either side. So if I'm having trouble with problem 3, work problem 2, work problem 4, and see if you can figure out the concept that you're having trouble with, because it may give you a clue as to how to look at problem 3. So the homework is just the bare minimum problems that we ask you to do. Okay? Homework's just the bare minimum problems, but the way to understand physics and the way to get through this is to look at the variety of problems that you have so that you can catch what's going on. The other part about this is, by looking at the section in the text, go look at the examples. Because the examples are looking at the concepts that are being explained in that section of the text. So you really want to look at the examples to help you out. So that's a way to get more sample problems, how to do it, look at it. Because how many of you use the watch it and you go, okay, I followed it just like the watch it in WebAssign, but I still get the wrong answer? Do I have nods of heads? Mm-hmm. And what do you usually find out? They've left out a step. Or they've left out a crucial step, and it's related to a half, or it's related to a number, or it's related to how they set up the equation. And unless you go look at the problems above and below, you may not ever figure out what that step is. Classic example would be when I do cosines and sines. One is cosine, like cosine of 30 degrees, or cosine of 60 degrees. One of those, you end up with a number of a half, and they just plug it in, okay? And you never see it. They always leave out critical steps. They always leave out critical steps. So you want to kind of figure out what it is that you're doing and what it is that you're looking at in order to get there. All right, the suitcase problem is on Blackboard. I've added a whole bunch of other texts that are there, or other problems, sample problems, those kinds of things. You also have in WebAssign, you've got 2 tutorials. These are problems in WebAssign for chapters 4 and 5. They have a due date of 10/20, which is Friday during spring or during fall break. Okay. I did not go ahead and modify the due date because, first of all, these are worth 0 points. Okay, they're there just to help you out, get ready to study for the test, because the test is next Wednesday. So it gives you a variety of problems that you can work in order to help get ready for the test. And it's open. They're open until the 20th, so that you've got them out there. But those are just extra problems to help you study for the test. I haven't changed them. You will also probably notice, as of this morning, the next couple of chapters have popped up. So if you want to work ahead, you certainly can, because we are getting ready to start momentum today, and we're getting ready to start some of the other things that are happening, and we're right on track. So hopefully that gets you pretty well straightforward. I will give you an idea of what's going to be on the test on Friday, because I'll have it written up by then. So questions? Because Friday you've got energy homework. Homework's due to energy. It's out there. I am around today, but I got a couple of meetings today, so I don't know that I will be responding to email, but I will also be around tomorrow. So if you have issues and need an email, you certainly can do that. And everybody has access to tutor.com. I haven't seen anybody panicking about their time on tutor.com. So if you need something associated with that, holler for that too.
We get a sheet for test again.
Yeah, and you can make up your own 8.5 by 11 sheet, your own handwriting, whatever equations, things that you think you need to have for the test.
One side, right?
Just one side. Yep. And just one side.
So that 4 tutorial and that 5 tutorials not worth anything.
No, they're not score. Yeah, the tutorials score-wise aren't there. So if you know that there's one concept that you're having trouble with, those would be the problems I'd go work. You know, if you know you're having stuff that you're stuck with, those would be the problems that I'd work. Other questions? Okay, let's start. Friday will be video day, because I have a series of videos that help with this. I will warn you all right now. Momentum. There are a couple concepts in physics that you either get, and it's like, why doesn't everybody else get it? Or you don't. Okay, and this is one of those concepts that we're gonna experience. So do not be afraid to ask questions, because it will sound like I get snippy on this one, but I'm more frustrated at myself than I am at anybody asking a question. So definitely ask a question, because I'm trying to figure out how to explain this to somebody who it's in the category of that's hard for them to wrap their head around. And I will tell you, I've been working with this for a long time, because my son, who's also a science major, he's more you guys type. He actually does, he's in grad school, and he's doing experimental psychology and biochemist type, and he doesn't get it. And we have worked at it, and we can't quite figure out what the difference is. We're getting into the concept of momentum, all right? And for me, and really what I have found is momentum is black and white. You either see it as black or you see it as white. And there is no gray area. You know, with forces, things get a little gray. I can give you some examples, and you might figure, you know, you can get there. But momentum, just quite not like that. And I haven't quite figured out why. Because to me, it is straightforward. Totally straightforward. So let's talk about Newton's second law. Let's go back to Newton's second law. So Newton's second law, we said that the force net is equal to the mass times my acceleration. And that's the common form of Newton's second law. But that's really not what Newton said. Okay? That's really not what Newton said. Let's look at what Newton was trying to explain. So Newton, we have the Earth here, and we have the moon, And the question is, well, gee, why do the Earth and the moon come together? If I take a little apple and I drop it, it's going to fall right to the Earth. Why doesn't the moon fall right to the Earth? So that's one of the questions that's trying to be answered. And they've done a lot of data, and they took a lot of data. So Newton came up with this particular expression. And Cavendish actually went and did the experiment. And it shows that this force is related to the pull between mass 1 and mass 2, whatever those masses are, divided by how far apart they were squared. So this is Newton's universal gravitation. All right? So if I'm looking at the Earth-Moon system, so I get gravity, the mass of the Earth, the mass of the Moon, divided by the distance between the Earth and the Moon squared. If I take this right here, because no matter what other mass I deal with, okay, no matter if this isn't the Moon, let's say it's my apple, let's say it's something else, no matter what I deal with, the mass of the Earth isn't changing, and the radius of the Earth isn't changing. Okay, if I'm very close to the radius of the Earth, and this distance compared to the radius of the Earth is very, 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 very small. Yeah.
Are you dividing the radius by gravity as well, or is it just the two masses?
No, well, it doesn't matter. Mathematically, if I write it like this, there's no difference. Mathematically, there's no difference how I write it. We typically just write it, we write it with the big G, M1, M2 over R squared. That's just, convention as to how it's written. But there's no mathematical difference from writing it this way or writing it that way. Okay? One of the reasons is because this is a constant, and a lot of problems I can get rid of that constant. So I can play with it a couple of different ways. But this right here, if I look at the big G, the mass of the Earth, the radius of the Earth, that becomes my acceleration due to gravity, little g, what we normally experience at the surface of the Earth. So this is a special form of that right there. There's no real, it's just that commonly on the surface of the Earth, we're going to work with this one. If I'm dealing with planets and I'm dealing with the moon, I'm dealing with asteroids, I'm sending Voyager or V'ger, depending on if you watch the old Star Trek movie. V'ger, right? V'ger comes back eventually. So if I do all of that, this is the equation I'm going to use. But let's look at this a little bit more detail. So we're going to look at that in a little bit more detail. So this is what we said was Newton's second law. That's not what Newton said. Okay? That's not what Newton said. Newton said, and let's look at this. Newton actually says, I have something called an impulse, and I have momentum. And we talk about inertia. So I have three terms that we talk about: impulse, momentum, and inertia. Inertia is, I have my box, all right? I have my box, and this has a little mass m, or I have my box, and it has a bigger mass m. Which one of those has more inertia? How am I going to get it to move, right? When I talk about inertia, which has more inertia, I'm going to have to apply more force to get that one to move than I do that one. Because that mass is bigger, and inertia is related to the mass of the object, okay? In fact, Newton defined mass in terms of inertia. So the more massive something it has, the more inertia it has. All right, so we know that. So he says, okay, But we also know from Newton's first law, an object in motion remains in motion unless acted upon by another force. So I've got to do something in order to have it act upon by a force. And we apply forces two ways. We apply forces as a steady force. We apply forces as a field force. And we talked about that kind of. We said, well, we've got field forces. Gravity would be a field force. And when you get to physics 2, we'll talk about things like electricity, and we'll talk about things like magnetism. God, I can't spell today. And we know about magnetism. If I take a magnet and I have a north pole and a north pole of my magnet, they repel each other, right? If I try to bring two north poles of my magnets together, you can feel it. You can feel that repulsive force. Well, gravity, we don't feel it because we experience it all the time. So we kind of ignore it, but we have those field forces. But now if we apply a force, like to a hockey puck, okay, we hit it with the hockey stick, we don't apply the force the whole time. It's not a steady force. If I hit a softball with a softball bat, if I hit a baseball with a baseball bat, if I kick a soccer ball, if I kick a football, we're applying a force only for the briefest amount of time, right? We're applying a force for the briefest amount of time. We actually apply what we call an impulse, okay? When we're doing that, we actually apply what's called an impulse. So Newton actually said this. Newton actually said that we have an impulse, and the impulse is my force times my time, my change in time. And this is defined as an impulse. So I'm going to apply that force over a brief amount of time. Okay. He also said that force was equal to a change in momentum. So my force is equal to a change in momentum. So an object in motion remains in motion unless acted upon by a force. So when I deal with my force, my change in momentum, we define momentum. Momentum is a vector quantity. Okay, it's a vector quantity, and we usually use the little letter P to do that. We define momentum as mass times velocity. So my momentum is going to be in the same direction as my velocity. So if I look at that and I have my momentum and I keep on going in my change in momentum, I can rewrite my force equation as this. So I've got my force is equal to my change in momentum, and now I'm going, okay. Somehow I'm thinking I've left something out.
So it'd be,
My impulse is going to give me my change in momentum. Yeah, there we go. I've left something out. Knew ahead. I'll show you why I knew I had left something out. So my impulse is going to give me my change in momentum. So my impulse is related to my change in momentum, but if I take that change in time,
is that delta M mass or momentum?
this is momentum, okay?
So on the, what's the vector P?
The vector is only on velocity. Mass does not have a vector.
Right there, it's mass times.
This is momentum, is mass times velocity. So P is momentum.
And
M is, this isn't momentum. That's mass.
On the one on the bottom, it's momentum.
Well, down here, that's mass. Mass times velocity. This is momentum. So I could write this as a change in P. Okay? Are you guys with me over there in Enid? Okay. All right. So my impulse gives me a change in momentum. All right. My impulse gives me a change in momentum. So I'm going to clean this up since I've scribbled all over it. so it looks nice and neater. So my force times the change in time is going to equal my change in momentum. So I'm going to write it that way, and now I've got to change mv. Okay? I'm going to divide both sides by delta t, so my force is going to equal my change in momentum with respect to time. Now, I'm going to apply this change to my different things. So I'm going to do this, and if I do apply that change, what I end up with is I could have a change in mass times velocity over time, and I can have a change in velocity times mass over my change in time. But what's my change in velocity over my change in time? Yep, it's acceleration. Okay, so now I've got mass times acceleration plus, I'm going to have my velocity divided by my change in time and a change in mass. Oops. Our second law is missing a term. Because this is what we usually refer to as our Newton's second law, right? This is usually what we refer to as our Newton's second law. We got a problem. There's this extra term out here. Well, most of the time, when I'm working problems, does my mass change? Most of the time, my mass doesn't change. So this term I don't have to worry about because I don't have a change in mass. Most of the time.
So that's like constant?
Well, it's zero because I don't have a change in mass. My mass doesn't change. No change in mass, it's zero.
But technically that is.
So if I have no change in mass, technically that's zero. So I don't have to worry about that extra factor. Except when? We look at the broader term of Newton's second law. When? So if I look at the space shuttle, when it first takes off, my space shuttle is sitting on a rocket. Right? I do have a change in mass when I'm dealing with the space shuttle because I'm consuming a heck of a lot of fuel. This is a heck of a lot of mass that's sitting out there that I have to worry about. So when I'm dealing with things like rocket science, this is where it comes from. This extra term that we normally don't think about for Newton's second law, because Newton's second law is really this right here. Newton's second law is really that the impulse is equal to the change in momentum, and I can look at that change in momentum, and I can get the things that are going back and forth. So this is more of what Newton was saying in the second law, rather than this here, but for practical terms, this is what we see most of the time. For practical terms, that's what we see most of the time. And I think that's getting us really close to time because I don't want to start anything else. But I wanted to get us started with momentum because momentum gets to be fun because now we get to crash things. We get to make things crash and come together. So, alrighty. We'll see you all on Friday.
Okay.